Hello, so this is the Posicast control journey. This is the video 9, and we are going to speak about PID control with Posicast. This is the part 3 regarding the PID control. So we have seen before the control structure that we are using. This is a 2 degrees control structure that we got here a pre-filter, this GF, who is dealing with the reference input shaping. And we got a PID controller, and the pre-filter can be a Posicast, that in this case is an outside Posicast, but it can be a 3-step Posicast. And this is the PID control transfer function, and it uses a filter in series. This has been the design of this control system using the gravitational search algorithm has been reported in this first publication. And the problem about the sensitivity of this input shaping technique, Posicast, regarding parameter uncertainty was reported in the second one. So in this one, we are going to first to show you about what is the problem. The problem is, as you can see here, we got two responses. The first one in black is the tune response, and in dash red without retuning. We are going to insert a model, a parameter uncertainty in the time delay. And as you can see, after this instant, in the time equals 12 seconds, the response becomes quite oscillatory, and the system is behaving quite badly after the disturbance, in this case the model uncertainty. So to deal with this, we have proposed this technique. This is a technique where we have to have a model of the process, GM. This is the process. This is the difference between the model and the process. And depending on this error, we have to take a decision about to retune the controller. To retune the controller, you need to identify a new model, and then we got to design both the pre-filter, both these three parameters, the steps, amplitudes, and the time for the second step, and the PID controller gains. Okay, so we have shown in the last video the simulation results, and now we are going to present you a practical experiment. The practical experiment was reported in this paper here. It was presented in PID 2018 in Ghent, and it is an electronic circuit. The electronic circuit is a filter. This filter is known as the Sallen key filter, and in this case it was implemented with this operational amplifier LM741, which is a classic. This we can show by doing the analysis of this circuit that the transfer function, which relates the voltage at the output, VO, to the voltage in the input, so the signal in the output to the signal in the input, in the Laplace domain, can be represented with this model. A second order model, where we got this is a gain, and we got two parameters, A0 and A1. Okay. So this can be rewritten in this format, where we got here the natural frequency, as it is normal. So, and here we got this key is the quality factor. Okay, this is a way of expressing the underdamped second order transfer function. Some of the values for the capacitor C2 is this one, 689 nanofarads. These are the resistance of the R1 and R2. And here I'm going to show you, it's missing here. Okay, so in this case we are going to consider two cases. We have in the formula C1. C1 can be this C11 if we close this switch, and it can be this C12 if we close, instead of this, the second switch. So we are going to tune the controllers for this first capacitor, and then we are going to open this and close this to change for the second one. Okay, the first one is this value, and the second value is this one. So I'm not going to go to details, but you can easily obtain these values. So the gain, if you select these resistors R4 and R3 in the appropriate way, we can make this gain approximately 1. That's what we're going to consider this 1, okay, because of this selection of these resistors. This is usually is a potentiometer, and this is a fixed resistor, and this is tuned, so this is 1. Also, by analysis, we can determine the A0 in function of C1, C2, R1, and R2, A1 in function also of the resistors and the first capacitor, the natural frequency, the quality factor, and the damping factor. Okay. So if you use the C11, this value, this is the second order transfer function that we obtain. Okay, and if we use the second one, this is the transfer function that we obtain. Okay, so this is wrong. Don't forget about this. And so the methodology used is this one. So we have the system, the electronic circuit, it is in this part here, connected to a data acquisition card. This data acquisition card was the National Instruments ADDC acquisition board. This is the PCI E6361, and then we use that to connect to the MATLAB Simulink, where you do the controller design, the system identification, and also the optimization. The sampling time used was this one, 0.11 second, and we allow the control signal to vary between minus 10 volts and plus 10 volts. So we can represent the methodology as this one. Okay, if we don't have an uncertainty detection, we continue with the system as it is running. And but if you detect that the model has changed, then we have to do the identification of a model again, and then we have to use that model to run an optimization and update the controller gains or parameters, and then back again to the system. So this is the way that the system was executed. So just to show you, when we change from GP1 to GP2, and we got this, we use the derivative of the error. So we got this spike here, that you can see here. So we use this to trigger the system identification and the retuning action. And in this case, this system was changed from GP1 to GP2 from 8 seconds to 10 seconds. And okay, we neglect this part, the first part, 5 seconds, okay, because of the initial oscillation. And we use the threshold of 5 volts to trigger the tuning about this derivative of the error. Okay, so in this case, the identification outcome was this model for GP2, this here with an hat, and designing the Posicast and the PID controllers respecting these intervals from the parameters, from A1 for the time of the second step and from the controller gains. In this case, actually, there was not a change. The parameters for A1, A2, KP, KI were the same, Of course, the time from the second step change from point 8 to point 2 to point 8, and also the KD change a little bit. Okay, and just to show you the result, you can see that if you use the controller 1 and then we change the model without retuning, this is the response with the first controller, and then with the second controller, okay, the system behaves much better. So this is the advantage of retuning and using that technique that I show you about. So with this thing I conclude the video 9, and I hope that you enjoyed it.